Hello friends, in our previous lecture we discussed the various parameters and properties of sine wave. We learnt that the sine wave is a time varying periodic waveform. Alternating current changes direction in response to changes in the polarity of the source voltage. One cycle of an alternating sine wave consists of a positive alternation and a negative alternation, and finally we learnt that the two sources of sine waves are the electromagnetic AC generator and the electronic oscillator circuit. In today's lecture we shall be talking about the various voltage and current values of a sine wave, how to find the instantaneous value at any point, find the peak value, find the peak to peak value, define RMS, why the average value is always 0 over a complete cycle, finding the half cycle average value, angular relationships of sine waves, how to measure a sine wave in terms of angles, define radian, convert radians to degrees, determine the phase angle of a sine wave. Sinusoidal voltage and current values. 5 ways to express the value of a sine wave in terms of its voltage or its current magnitude are instantaneous, peak, peak to peak, RMS and average values. Instantaneous value. Figure here illustrates that at any point in time on a sine wave, the voltage or current has an instantaneous value. This instantaneous value is different at different points along the curve. Instantaneous values are positive during the positive alternation and negative during the negative alternation. Instantaneous values of voltage and current are symbolized by lowercase v and I respectively. The curve in part A shows voltage only, but it applies equally for current when the V's are replaced by I's. An example of instantaneous values is shown in part B, where the instantaneous voltage is 3.1 volts at 1 microsecond, 7.07 volts at 2.5 microseconds, 10 volts at 5 microseconds, 0 volts at 10 microseconds, minus 3.1 volt at 11 microseconds, and so on. Peak value. The peak value of a sine wave is the value of voltage or current at the positive or the negative maximum with respect to 0. Since the positive and negative peak values are equal in magnitude, a sine wave is characterized by a single peak value. For a given sine wave, the peak value is constant and is represented by V peak or I peak. Peak to peak value. The peak to peak value of a sine wave, as shown in figure, is the voltage or current from the positive peak to the negative peak. It is always twice the peak value as expressed in the following equations. Peak to peak voltage or current values are represented by VPP or IPP. VPP is equal to 2V peak and IPP is equal to twice I peak. RMS value. The term RMS stands for root mean square. Most AC voltmeters display RMS voltage. The 220 volts at your wall outlet is an RMS value. The RMS value, also referred to as the effective value of a sinusoidal voltage, is actually a measure of the heating effect of the sine wave. For example, when a resistor is connected across an AC voltage source, as shown in part A of figure, a certain amount of heat is generated by the power in resistor. Part B of figure shows the same resistor connected across a DC voltage source. The value of the DC voltage can be adjusted so that the resistor gives off the same amount of heat as it does when connected to the AC source. The RMS value of a sinusoidal voltage is equal to the DC voltage that produces the same amount of heat in a resistance as does the sinusoidal voltage. When the same amount of heat is produced in both setups, the sinusoidal voltage has an RMS value equal to the DC voltage. The peak value of a sine wave can be converted to the corresponding RMS value using the following relationships for either voltage or current. Vrms is equal to 0.707 V peak and Irms is equal to 0.707 I peak. Using these formulas, you can also determine the peak value if you know the RMS value. V peak is equal to V RMS over 0.707. Then V peak becomes equal to 1.414 V RMS. Similarly, I peak is equal to 1.414 I RMS. To get the peak to peak value, simply double the peak value. Vpp is equal to 2.828 V RMS and Ipp is equal to 2.828 I RMS. Average value. The average value of a sine wave taken over one complete cycle is always 0 because the positive values, that is above the 0 crossing, offset the negative values, that is below the 0 crossing. To be useful for certain purposes such as measuring types of voltages found in power supplies, the average value of a sine wave is defined over a half cycle rather than over a full cycle. The average value is the total area under the half cycle curve divided by the distance in radians of the curve along the horizontal axis. The result is expressed in terms of the peak value as follows for both voltage and current sine waves. V average is equal to 2 by pi into V peak. So, V average becomes 0.637 V peak. Similarly, I average is equal to 2 by pi into I peak and it becomes 0.637 I peak. Angular measurement of a sine wave. As we have seen, sine waves can be measured along the horizontal axis on a time basis. However, since the time for completion of a one full cycle or any portion of a cycle is frequency dependent, it is often useful to specify points on the sine wave in terms of an angular measurement expressed in degrees or radians. The sinusoidal voltage can be produced by an AC generator. As the windings on the rotor of the AC generator go through a full 360 degrees of rotation, the resulting voltage output is one full cycle of a sine wave. Thus, the angular measurement of a sine wave can be related to the angular rotation of a generator. A degree is an angular measurement corresponding to 1 upon 360 of a circle or a complete revolution. A radian is the angular measurement along the circumference of a circle that is equal to the radius of the circle. 1 radian is equivalent to 57.3 degrees as illustrated. In a 360 degree revolution, there are 2 pi radians. The Greek letter pi represents the ratio of the circumference of any circle to its diameter and has a constant value of approximately 3.1416. Table here lists several values of degrees and the corresponding radian values. The angular measurements are illustrated in this figure. Sine wave angles. The angular measurement of a sine wave is based on 360 degrees or 2 pi radians for a complete cycle. A half cycle is 180 degrees or pi radians. A quarter cycle is 90 degrees or pi by 2 radians, and so on. Phase of a sine wave. The phase of a sine wave is an angular measurement that specifies the position of the sine wave relative to a reference. Figure shows one cycle of a sine wave to be used as the reference. Note that the first positive going crossing of the horizontal axis is at 0 degrees or 0 radians, and the positive peak is at 90 degrees or pi by 2 radians. The negative going 0 crossing is at 180 degrees or pi radians, and the negative peak is at 270 degrees or 3 pi by 2 radians. The cycle is completed at 360 degrees, that is 2 pi radians. When the sine wave is shifted left or right with respect to this reference, there is a phase shift. In part A, sine wave B is shifted to the right by 90 degrees or pi by 2 radians with respect to sine wave A. Thus, there is a phase angle of 90 degrees between sine wave A and sine wave B. In terms of time, the positive peak of sine wave B occurs later than the positive peak of sine wave A, because time increases to the right along the horizontal axis. In this case, sine wave B is said to lag sine wave A by 90 degrees or pi by 2 radians. Stated another way, sine wave A leads sine wave B by 90 degrees. In part B of figure, sine wave B is shown shifted left by 90 degrees with respect to sine wave A. Thus, again there is a phase angle of 90 degrees between sine wave A and sine wave B. In this case, the positive peak of sine wave B occurs earlier in time than that of sine wave A. Therefore, sine wave B is said to lead sine wave A by 90 degrees. As a practical matter, when you measure the phase shift between two waveforms on an oscilloscope, you should make them appear to have the same amplitude. This is done by taking one of the oscilloscope channels out of vertical calibration and adjusting the corresponding waveform until its apparent amplitude equals that of the other waveform. This procedure eliminates the error caused if both waveforms are not measured at their exact center. The sine wave formula. A sine wave can be graphically represented by voltage or current values on the vertical axis and by angular measurement along the horizontal axis. This graph can be expressed mathematically also. A generalized graph of one cycle of a sine wave is shown in figure. The sine wave amplitude A is the maximum value of the voltage or current on the vertical axis. Angular values run along the horizontal axis. The variable y is an instantaneous value that represents either voltage or current at a given angle theta. All electrical sine waves follow a specific mathematical formula. The general expression for the sine wave curve in figure is y is equal to a sin theta. This formula states that at any point on the sine wave represented by an instantaneous value y is equal to the maximum value a times the sine of the angle theta at that point. For example, a certain voltage sine wave has a peak value of 10 volts. You can calculate the instantaneous voltage at a point 60 degrees along the horizontal axis as follows, where y is equal to V and A is equal to V peak. V is equal to V peak sin theta and is equal to 10 volts into sin 60 degrees, and this comes out to be 10 volts into 0.866 and is equal to 8.66 volts. Figure shows this particular instantaneous value of the curve. You can find the sine of any angle on most calculators by first entering the value of the angle and then pressing the sine key. Verify that your calculator is in degree mode. Expressions for phase shifted sine waves. When a sine wave is shifted to the right of the reference, that is lagging by a certain angle phi, as illustrated, where the reference is the vertical axis, the general expression is y is equal to a sin theta minus phi, where y represents instantaneous voltage or current and a represents the peak value, that is amplitude. When a sine wave is shifted to the left of the reference, that is leading by a certain angle phi as shown in part B, the general expression is y is equal to a sin theta plus phi. So friends, this brings us to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt to determine the various voltage and current values of a sine wave, find the instantaneous value at any point, find the peak value, find the peak to peak value, define RMS, explained why the average value is always 0 over a complete cycle, found the half cycle average value, described angular relationships of sine waves, showed how to measure a sine wave in terms of angles, defined a radian, converted radians to degrees, determined the phase angle of a sine wave. So that is it for today. See you in the next lecture, and we shall be discussing about phasors. Thank you very much.